Good morning. So now we are going to discuss about some material from the Laplace equation. So in this set of lectures, we have two things. One is about the Perron's method of existence of boundary variety problem, and then we will also discuss about the Newtonian potential, namely potential theory related to existence of Laplace equation. So in this first lecture, we will recall about the Laplace equations as in some of its properties, which we have discussed in the PDE 1 course. Okay, so let me recall. So this lecture is going to be the review of PDE 1 about the Laplace equation. We just recall the results. So if you are not familiar with it, you should go through before continuing this course. So let's recall our problem of study. Recall our problem. So you have an omega subset of Rn, open set. Most of the time we will see bounded open set, but start with this omega open set in Rn, and you are interested in studying minus Laplacian u equal to f in omega and u equal to g on d omega. So this is the problem. This problem we call it as what? Okay, where f and g are given. F is g given. We normally assume some conditions which we will discuss with you as we proceed. So f and g are given. So the problem is that find u in appropriate spaces. Find u. Basically you want to find u. A classical solution, it should be C2 of omega to define what is Laplacian of u, and it should be intersection of C of omega bar. So you need continuity up to the boundary because you want to define what is u equal to g. Okay, so this problem can be solved. We can write, these are all we have discussed last time. We can write u is equal to, we split this problem into two problems. That's how we are going to study, where we will satisfy a homogeneous equation, Laplacian of u, that is means, this should be v. V is harmonic. V is harmonic. That is homogeneous equation. Homogeneous with non-trivial g. So you will see non-trivial boundary condition. Okay. On the other hand, w satisfies minus Laplacian of w equal to f and w equal to 0 on d omega. This is in omega and this is it. So this is your problem 2. I will be recalling. This is your problem 3, and this is called the potential theory. So we will study about that. So we will split our lectures into two parts. One is about the potential theory, the other one, but trivial boundary condition. So this is a trivial boundary condition, but non-homogeneous data. Non-homogeneous, this equation. Homogeneous. And this is what eventually, after studying, we will not do it in this course. Then there is more general theory about Schauder theory. Schauder theory of second order elliptic operators. Second order elliptic. So, okay, if you want to understand this one, you can see the reference Gilbert and Truding. If you want to see more about Gilbert, Truding. Okay, here this is what we are going to do first in the beginning. This is what we are going to study. You have seen some special problems in the upper half plane and a ball. we will do it more general omega. This is in omega, this is on d omega. D omega is the boundary. So you have typically domain omega, this will be going omega, and you have your d omega. This we will prove the existence via Perron's method. Things are bit delicate, so we will try to motivate you some of the things here. Okay, so this is what we are going to do. So maybe this we will finish off Perron's method in 3 or 4 lectures, and another 5 lectures or something we will do potential theory. So basically we will do the extension of what we have studied in the last PDE1 course, around 9 to 10 lectures. So let me recall some of the things now. This is what essentially we are going to study. So recall in that one, the one of the first thing we have introduced is fundamental solution. Fundamental solution. Okay, so go through it. What is the fundamental solution of minus Laplacian? So what we have introduced Fex, which has a singularity at the origin. This is minus 1 over 2 pi log mod x. In the case of dimension 2, it depends on dimension, and then otherwise 1 by n into n minus 2 omega n modulus of x power n minus 2. This is when n greater than or equal to 3. So this is the volume of the unit ball. Volume of unit ball of radius 1 V10 in Rn. Okay, so that is how, and this has a singularity. Phi has a singularity at the origin. And we know that phi is harmonic. Phi is harmonic in Rn minus 0. So you see, except at the origin, it is harmonic. That is Laplacian of phi. We write it minus always equal to 0 in Rn minus 0. You see. But in modern language, which we may not study here, but we may hint at the end of this course little bit about it. In modern language, it is called minus Laplacian of phi equal to Dirac delta at the origin in Rn. This is in distribution theory. We will tell you later. We already mentioned this. What is the meaning of this, or probably we will do it in distribution sense. Okay. So that's what we have done. So minus Laplacian, and you have done a lot of problems in this previous case. What are the troubles and advantages? If you look at it, the function phi, even though there is a singularity, phi and grade B singularity are not serious. Even though there is singularity, these are locally integrable. Locally integrable. But when you go to second derivative, all the second derivative is not locally integrable. That's why you cannot take it locally integrable. You see? So the first result we have proved is in this direction. One result we have proved immediately after introducing, if f is in twice continuously differentiable function with compact support, it's not a boundary value problem, it is in that, then if you define u as the convolution with phi satisfies minus Laplacian of u equal to f in Rn. So you recovered the source term by convolving with it. So this is one result we have proved. But the major study in the previous course about various properties about it. One of the important thing we have studied what is called mean value property. Mean value property of harmonic functions. Harmonic functions. What is that? Laplacian of u equal to 0 implies mean value property implies u satisfies mean value property. Mean value property. That is, if you have a domain here, you have any point x here, you take any ball of radius r, you can compute your value. In fact, these are all if and only if property basically. Eventually, we have seen that this is if and only property. You can compute u of x is equal to, let not mention that one, u of x is equal to the average of b over b. This is the ball of any ball of radius. Okay, ball of radius r, you integrate over b of r u of y dy. This is also equal to, you can average it out on the boundary of the ball. Ball integral over br u of y d sigma y. This you integrate with respect to the surface measure. In fact, you have inequalities for Laplacian of u greater than or equal to 0 and Laplacian of u less than or equal to 0. These are called sub-harmonic. You will see more general definition of sub-harmonic function later in Perron's method in the next class. Okay, this is called super-harmonic. We have motivated enough these things in the class PDE 1 course. Okay, so if u is a harmonic function and then u satisfies this one, and it is a if and only property, that means the converse is also true. Converse is also true. That is, you can see that is, if u is harmonic, you have this equality, but you can, if this satisfies for all continuous function. The advantage is that to define these functions, you don't need the differentiability of u. To define mean value property, so to define mean value property, u is in C2 is not necessary. You see, continuity is enough. That's what you have to see, that continuity is enough. So the mean value property actually gives you the smoothness of the process. That means, that is, okay, mean value property. So I will not state everything which you there, otherwise you can refer the book and recall everything. Mean value property satisfied for continuous function. For a continuous function, u for all ball inside contained completely in omega. You should not be boundary. So you have for all balls mean value property is satisfied, then you can actually show that Laplacian u equal to 0. That's what. And in fact, you can actually show that u is C infinity, and you can also get analyticity. So you see, you can prove all that. In fact, we have proved all these facts in the last class. Okay, that's what about the mean value property. And another important thing we proved in the last class is maximum minimum principles, because we are going to use all this maximum and minimum principles. Minimum principles. So let me only write the maximum principle, but you can also write down the minimum principle. So in this case, if omega bounded, connected, then U sub-harmonic then you cannot have an interior maximum unless U is a constant. Cannot have an interior maximum, that is a maximum point inside, unless U is a constant. Unless U is a constant. Of course, constant means every point is a maximum and every point is a... If U is not a constant function and if it's a sub-harmonic function in a connected bounded set, then it cannot have an interior. This has far-reaching implications, and in fact, you can... this also implies immediately, if you look at your supremum of U is bounded up to the boundary, so supremum exists, your supremum you are taken in omega will be the same as maximum in omega U in omega bar, and the maximum, since omega bar is a closed bounded set, it will have a maximum in omega bar, not in omega, and hence that maximum has to be on the boundary. So you will get this is same as maximum over U on the boundary. You see, similar results for similar results for super-harmonic functions. So in the case of super-harmonic function, it cannot have an interior minimum, okay, harmonic function. And if U happen to be harmonic, it will not have an interior maximum and it cannot have an interior minimum, and the minimum and maximum attained on the boundary. Okay, using this we have immediately proved uniqueness of our initial boundary value problem. Uniqueness for boundary value problem 1, which we have proved in the last class. After that, this is what about the maximum principle we have proved, and many other results we have proved in our PDE1 course. After that, we have introduced what is called a Green's function. Green's function and representation formula. Representation formula. So Green's function we have introduced as a two-variable function gx, same singularity as fundamental solution, same singularity, same type of singularity. Singularity, you know that even though fundamental solution has a singularity and it is not a harmonic function in the entire plane, it provides solutions. In one of the results we have proved that using fundamental solution, you got the solution actually. Okay, so that singularity provides you solutions. It's capture the source term, recover the source term via the thing. So singularity, same singularity as that of fundamental solution. So this is gxy have the same singularity at x equal to y of that one. And what is additional thing? And further, okay, G takes care of the boundary condition, takes care of, because phi you have not imposed any boundary condition, but here G also takes care of the boundary condition. So we have explained all that thing, but let me not get into all that details here, but you should understand this Green's function, etc. So with this, it provided representation formula. Representation, okay, formula. That's the important thing. So this is a representation in the sense, if you solve one in a classical way, solves the problem, the boundary minus Laplacian u equal to f and u equal to g in omega, then u has a representation. That doesn't mean that it's only a, if you solve, you see this one. That doesn't mean that this will be a solution. We will make this thing immediately. Us has a representation. This is in omega f of y g of xy dy minus integral over d omega g of y dg by d nu. This is the normal derivative of xy and integrated with respect to the surface measure. So you see, so you have your representation formula here. And then in general, finding g is hard. Finding g is as difficult as that of finding u. As difficult as that of finding u. Then what is the advantage? Why did we introduce g but can find g for special domains? That's the thing. Can find g for special domains. Like a ball, like the upper half plane, like omega is equal to the upper half plane Rn plus, or omega is equal to a ball of any ball, in fact, a ball of radius. Use this to construct solutions here. So we use it to construct solutions. Use it to prove solutions, and that's the whole idea which we will be doing here. So before completing today's talk, so let me two cases let me do when omega is equal to Rn plus, and if you define the kernel, this is called the Poisson kernel kxy. These are all again introduced there. So you define kernel is equal to 2xn by n omega n mod x minus y power n. This is the kernel for xy in Rn plus. So you see, this is your Rn plus. This is your domain Rn plus, and this is your domain boundary Rn plus, okay, which of course can be identified with Rn minus. Okay, so you have that one, and with this you can write, you define by the representation formula, define u of x is equal to integral over the boundary Rn plus equal to k of xy g of y dy. I am taking f equal to 0 because that's a Newtonian potential which we will study later, and then we have this is called the Poisson integral for the upper half plane. Poisson integral for the upper half plane. And then you have proved a theorem. What we have proved, if g is a bounded continuous function in Rn plus, boundary of Rn plus, then u solves minus Laplacian of u equal to 0 in Rn plus and u equal to g on the boundary. So you have proved an existence for using that fundamental solution because we expressly constructed the Green's function. Using that you have solved this one, and in fact we also get actually u is a C infinity function in Rn. So you actually have more smoothness. That's a property of your Laplacian. So you have proved one existence theorem. But we are going to do it for a general domain omega. And the second case we have proved is when omega is a ball. Omega is equal to a ball of radius r. In this case, your kxy, again the kernel, is defined to be r square minus mod x square by n omega n r, and then 1 by mod x minus y power n. You see, kernel, and you are in this case the Poisson integral. We use this Poisson integral in the Perron's method soon. Okay, in the next class you will use, and then you define a similar thing of ux. You can define the ux exactly like this. Okay, ux you can define to be on the boundary of the ball. So you have defined boundary of the ball of radius 0, k of xy, g of y, d sigma y. Okay, here also d sigma y on the bound, but here in this case you get it as dy prime. Okay, because it's a flat Rn minus 1, so you can combine what is Rn plus, and again you have the theorem, exactly the theorem, g belongs to continuous function on the boundary of the ball. Of course you don't have to see the boundedness now, because the boundary of the ball itself is a compact set, so it will be automatically solved. Then u solves minus Laplacian of u equal to 0 in Br of 0 and u equal to g on boundary of the ball. In fact you have again u and also u is in C infinity of Br of 0. So you said, so as I said, so this is all a brief about the PDE1 course which we have. PDE1 about the Laplacian what we have studied. So what we want to study now, there is not very easy. Wish to study existence of my Laplacian u equal to 0 minus or not doesn't matter in omega, and u equal to g on d omega. So what we introduce is Perron's method, and it's not true for all domains. You need, and what we need is the regularity of the results. So you need regularity of the domain. The regularity of the domain. The regularity of the domain means the regularity of the boundary. That is regularity. That is regularity of d omega. Okay. So in the next class, our aim is to start introducing the Perron's method, and for that the ingredients which we need is, one is about the kind of Poisson integral. We will be using the Poisson integral, and we will also define the definition of sub-harmonic and super-harmonic functions. with continuous functions using maximum principles. So I'll stop here. Thank you very much.